right. Okay, so let's do some reading on the topic of a two-stage, two-level segregated bit memory allocator. Paper from these guys from space. So now I kind of F up. All right. So let's get started. Let's do some reading and grab a piece of paper and the pen and see what we can learn about this of allocator. So, abstract. Dynamic storage allocation (DSA) algorithms play an important role in modern software engineering paradigms and techniques, such as object-oriented programming. Okay. Using DSA increases the flexibility and functionalities of applications. There exists a large number of references to a particular issue in the. However, the use of DSA has been considered a source of indeterminism in the real-time domain. True. Due to the unconstrained response time of DSA algorithms and the fragmentation problem. Nowadays, new real-time applications require more flexibility, the ability to adjust system configuration and workload changes and application configuration. This aspect adds new value to the definition and implementation of dynamic storage allocation algorithms. Considering these reasons, new DSA algorithms with a bounded and acceptable timing behavior must be developed to be used by real-time operating systems, RTOSs. In this paper, a new DSA algorithm called two-level segregated fit memory allocator (TLSF) developed specifically to be used by RTOS, is introduced. TLSF algorithm provides explicit allocation and memory blocks with a temporal cost of 1. So we're dealing with memory allocator inside a real-time OS, and they want constant time allocation. Or so good. Introduction. The study of dynamic storage allocation (DSA) algorithms is an important topic in the operating systems research and implementation area. It has been widely analyzed. Jointly with other basic computing problems like searching and sorting, memory management is one of the most studied and analyzed problems. Wilson et al. Wrote an excellent survey tutorial summarizing the research carried out between 1960 and 1995 about storage allocation. Well, due to the large amount of existing DSA algorithms, reader can get to think that the problem of dynamic memory allocation has been already solved. This can be true for most application types, but the situation for real-time applications is quite different. Real-time systems, it is needed to know in advance the operation time bounds in order to analyze the system's schedulability. The goal of DSA algorithms is to provide dynamically to the applications the amount of memory required at runtime. In general, these algorithms are designed to provide good average response times, whereas real-time applications will instead require the response times of the memory allocation and deallocation bounded. Of course, if an allocation takes too long in a real-time system, well, that's a problem because then your operation may not run and the whole machine has to stop and stuff like that. Additionally, dynamic memory management can introduce an important amount of memory fragmentation. That may result in an unreliable service when the application runs for large periods of time. It's important to point out that a fast response time and high throughput need to be taken into account in particular in real-time. The main requirement defines these systems to guarantee that most DSL algorithms have been designed to provide fast response time for the most probable case, achieving a good overall performance, although their worst case response time can be high or even bounded. For these reasons, most RTOS developers and researchers avoid the use of dynamic memory at all, or use it in a restricted way, for example, only during the system startup. Developers of real-time systems avoid the use of dynamic memory management because they fear that the worst case execution time of dynamic memory allocation routines is not bounded or is bounded with a too important bound. This paper introduces a new algorithm called TLSF for dynamic memory allocation that presents a bounded worst case response time, but keeping the efficiency of the allocation and deallocation operations with a temporal cost of O of 1. In addition, the fragmentation problem has higher impact in system performance with long time running applications. A small and bounded fragmentation is also achieved by the proposed algorithm. The following section reviews the set of real-time requirements that should be fulfilled by the DSA algorithms for real-time applications. Section 3 describes the fragmentation problem that appears in DSA. Section 4 gives an overview of the kinds of dynamic storage allocation strategies. Section 5 presents the general operational model of memory allocators. Section 6 details the main criticism and the main criteria the main criteria used to design the TLSF allocator. The structures and characteristics of the TLSF are presented in Section 7. Section 8 evaluates the algorithm. Section 9 compares the final results obtained by the proposal versus other approaches. Finally, Section 10 outlines our conclusion and future direction to work. real real-time requirements for DSA. One of the key issues in real-time systems is schedulability analysis to determine whether the system will satisfy the application's timing constraints at runtime or not. Regardless of the analysis and scheduling techniques used, it is essential to determine the worst-case execution time, WCT, of all the running code, including application code, library functions, and operating systems. Another characteristic that differentiates real-time systems from other kinds of systems is that real-time applications run for large periods of time. Most non-real-time applications take only a few minutes or hours to complete work and finalize. Real-time applications are usually executed continuously during the whole life of the system, months, years, and so on. This behavior directly affects one of the critical aspects of dynamic memory management, memory fragmentation problem. Considering all these aspects, requirements of real-time applications regarding dynamic memory can be summarized as bounded response time, worst case execution time, WCT, memory allocation and deallocation has to be known in advance and be independent of application data. This is the main requirement that must be met. Fast response time. Besides having a bounded response time, the response time has to be short for the DSL algorithm to be usable. A bounded DSA algorithm that is 10 times slower than a conventional one is not useful. Memory requests need to be always satisfied. Non-real-time applications can receive a null pointer or just be killed by the OS when the system runs out of memory. Although it is obvious that it is not possible to always grant all the memory requests requested, the DSL algorithm has minimized the chances of exhausting the memory pool by minimizing the. With respect to memory requirements, there exists a large range of RTSs. What? There an O missing? RTOS. Small embedded systems, very little memory, no virtual memory support, MMU, memory management unit, no permanent storage, too large redundant multiprocessors. Our study and the proposed algorithm focus on small memory is a scarce resource. There is no MMU support. Regarding the way allocation and deallocation are managed, you may find two general approaches for these. One, explicit allocation and deallocation. Allocation needs to explicitly call the primitives of the DSL algorithm to allocate memory. For example, malloc and release it when it's not needed anymore. And two, implicit memory deallocation, also known as garbage collection, where the DSL makes in charge of collecting the have been previously requested but not needed, or to make them available for new allocation. The paper is focused on explicitly low-level allocation primitives, garbage collection. So we're dealing with RTOS memory allocation. See whether that's our use. Fragmentation. Besides timing faults due to unbounded time, DSA implementation, memory allocation may fail due to memory exhaustion. Memory exhaustion may have two reasons. One, the application requires more memory than the total available in the system. Or two, the DSL is unable to reuse memory free. The DSA algorithm can do nothing in the first case. The application has to be redesigned of more physical added to the system. Historically, the second reason is considered as different aspects called internal and external fragmentation. Recent analysis considers fragmentation problem called wasted memory simply fragmentation has been considered a serious issue. Many initial experimental studies based on synthetic or random workloads conclusion that the fragmentation problem may limit or even prevent the use of memory. Johnstone et al. Showed that the fragmentation problem with real non-synthetic workload Not that not that graph can be efficiently managed by well-designed allocators. Not that grave and can be efficiently managed by well-designed. Their conclusion states that the fragmentation problem is really a problem of poor allocator implementations. Other interesting conclusions of the work are best fit or physical first fit policies low fragmentation. Blocks of memory should be immediately coalesced upon release and preferably reuse the memory that has been recently released over those blocks that have been released further in the results of Johnstone et al. Also showed that Zulea's allocator, which is a good fit policy, nearly best fit based on segregated fit policy, performs very well in terms of. Although Johnstone et al. Used non-real-time applications as workload, GCC, Go, Script, Perl, etc., there's no reason to think that real-time applications will show a behavior different enough to. The main difference between real-time and non-real-time applications is that many real-time applications do not use dynamic memory. Memory is statically allocated at start time, which is very safe. DSA algorithm. The goal of DSA algorithm is to grant the application the access of blocks of memory from a pool of free memory blocks. The different algorithm strategies differ in the way they find a free block of the most appropriate size. Historically, DSA algorithms have been be classified according to the following categories. Sequential fit. These algorithms are the most basic ones. They are based on a single or doubly linked list of all free memory blocks. Examples of algorithms based on the strategy are fast fit, first fit, next. Sequential fit is not a good strategy for RTOSs because for real-time systems, because it is sequential search, whose cost depends on the number of existing blocks. Search can be bounded, but the bound is not normally accepted. Segregated free list. Segregated free lists algorithms use an array of lists containing the references to free blocks of memory of a size or inside a particular size range. When a block is deallocated, it is inserted in the free list corresponding to its size. It is important to remark that the blocks are logically but not physically segregated. There are two variants of the strategy: simple segregated storage and segregated fits. Examples of Standish and Tadman's cast fit, which uses an array of several small size free lists and a binary tree free lists for larger sizes. And the DSA developed by Douglas Lea. Douglas. Oh man, some errors in these papers. No, they said do Lea. There, when a block is deallocated, is inserted into in the free list corresponding to size. It is important to remark that the blocks are logically physically segregated. There are two variants of the strategy which uses an array of several small sizes, small size free lists, and a binary tree for the free lists for larger sizes. And DSA developed by Douglas Lea. This strategy is acceptable to RTOSs since the searching cost is not dependent on the blocks. Body systems. Body systems are a variant of segregated free lists, efficient large operation. There are several variants of this: binary bodies with bodies and double bodies. Body systems exhibit good timing behavior, adequate for. They have the disadvantage of large internal fracture, up to 50%. Indexed fit. This strategy based on the use of advanced structures to memory blocks. Several interesting features. Examples of algorithms used by fit are a best fit algorithm using best fit allocator blocks, indices, size and memory address, etc. The indexed fit strategy can perform better than segregated free lists if the search time of a free block does not depend on the number of free blocks. Bitmap fit. Bitmap fit methods are a variant of indexed fit method. Use a bitmap to know which blocks are busy or free. An example of this method is the fit. This approach has the advantage with previous ones that all the information needed to search is stored in a small piece of memory, typically 32 bits, therefore reducing the probability of cache misses and improving the response time. Okay. A DSA operational model. Good. DSA operational model. DSA is an abstract data type that keeps track of which blocks of memory use and which must provide at least two operations allocated memory. Comments of a DSA mostly free blocks. In order to better understand the impact, it's interesting to analyze how most dynamic storage allocators manage free memory blocks. Initially, the memory that will be managed by the DSA is a single large block of memory, usually called the initial pool. It's also possible that the allocator relies on the underlying OS or the hardware MPU to request new memory to manage. First allocation requires blocks of memory pool. The initial pool is treated accordingly. Previous allocated block is reduced. Two things may occur depending on the physical position of the block. This block can be merged with the initial pool or with one or more free blocks. All the free block is surrounded by allocated blocks cannot be merged. In the first case, the DSA algorithm may coalesce the block or return to the pool. In the second case, the DSA algorithm inserts the free block in the data structure of blocks. If there are free blocks, then new allocation requests can be made by using the initial pool or by searching for a free block large enough to fit the size. The internal data structure of the free block is stored and the method used to block are the heart of DSA. Determine its performance. The free block used to fulfill the allocation request fulfill the allocation request is bigger than the requested. Then the block has to be split and the non-allocated part has to be returned to the data structure. Programs using dynamic memory invoke two operations: malloc, dynamically in a block of memory, and free to release the previous block. These operations are managed by the DSA algorithm, which requires to perform operations to manage free blocks, inserting, removing, and searching. These operations are now described in more detail. Insert a free block. This operation may be required by both free and malloc. In the first case, the inserted block is the one released by the application, or a larger one if it is less. In the case of malloc, the inserted block is the remaining part of the memory block that is larger than requested. Search for a free block of a given size or larger. It finds a free block large enough to serve the application request. As said above, criteria used to find the block, first fit, best fit, etc., how the DSA data structure design what mostly determines the performance of the DSA. Search for a block adjacent to another. In order to coalesce a free block, it is necessary to find the physical adjacent free blocks. Remove a free. This operation may also be needed both for free and malloc. The first case occurs when the block can be coalesced, in which case the free adjacent block is removed and merged with the free block. The second case occurs when malloc finds a suitable block in the 6. Design criteria of TLSF. There's not a single DSA algorithm suitable for all applications. Already stated, real-time application arguments are quite different from conventional applications. In this section, we design of a new algorithm called two-level segregated fit, TLSF for short, to fulfill the most important requirements: bounded and short response time, and bounded and low computation. Moreover, the constraints should be considered for embedded real-time systems are trusted environment. Programmers that have are not malicious, that is, do not try to intentionally steal or corrupt application data. Protection is done at the interface level, not at the programming level. Small amount of physical memory available, no special hardware available to support virtual memory. In order to meet these constraints and requirements, TLSF has designed with the following guidelines: immediate coalescing. As soon as a block of memory is released, TLSF will immediately merge it with adjacent blocks, if any, to build up a larger free block. Other DSA algorithms may defer coalescing, not coalesce at all. Deferred coalescing is a useful strategy in systems where applications repeatedly use blocks of size. Yes. In such cases, deferred coalescing removes the overhead of merging and splitting the system. True. Although deferred coalescing can improve the performance of the allocated, it adds unpredictability. A block request may require to merge an unbounded number of free but not merged blocks, and also increase fragmentation. Therefore, deferred coalescing should not be used. But splitting threshold, the smallest block of allocatable memory bytes. Most applications not an exception. Do not allocate simple data types like integers, pointers. More complex data which contains one pointer and by limiting minimum block size to 6 bytes, it is or inside blocks the information needed to manage them, including the list of free blocks pointers, which optimize usage. Good fit strategy. TLSF will try to return the smallest chunk big enough to hold the required block. Most applications only use blocks of a range of sizes. Best fit tends to propose for application on real-time workloads. Compared to other approaches, fit, best fit or almost best fit, also called good fit, strategy can be implemented in an efficient and predictable manner by using segregated tree lists. On the other hand, other strategies like first fit or next fit, depending on the sequence, first fit strategy generate in a long sequential search and generate in a long sequential. TLSF implements a good fit strategy that uses a large set of free lists where each list is a non-ordered list of blocks whose sizes between the size class, a range of sizes, and the next size class. Each segregated list contains blocks of the class. We assume that the original memory pool is a single large block of free memory and no SBR. Since general purpose OSs like Unix provide virtual memory, most DSAs plan to take advantage of it. By using this capability, it is possible to design a DSA all memory, delegating the management of large blocks to the underlying OS, dynamically enlarging memory pool. TLSF has been designed to provide support for dynamic memory, that is, it by application and also by the OS, no virtual hardware. Same strategy for all block size. Same allocation strategy. One of the most efficient and widely used Douglas-Leas uses 4 different sizes requested first. First fit, cache blocks, second list, and kind of algorithms do not provide a uniform behavior, so the worst case high or even different. Memory is not cleaned up. Neither the initial pool nor the free blocks are the DSA environments have to clean or to avoid security problems. Not cleaning what is allocated to the user is considered a serious security. Because a malicious program could obtain confidential. Really. Nevertheless, we assume that TLSF will be used in a trusted environment where applications are written by well-intended programmers. Therefore, initial memory is less feature overhead. Programmers should not use memory as good program practice recommend. TLSF data structure. Data structures used by the dynamic memory application described in this TLSF algorithm uses segregated fit map and a good basic segregated fit map array of free lists, with each array holding free blocks within a size. In order to speed access to free blocks and also to manage a large set of segregated lists, reduce fragmentation, the array of lists be organized as a two-level array. First level array divides free blocks in classes. That are a power of 2 apart, 16, 13, or 128, etc. Second level subdivides each first level class linearly, where the number of divisions referred to as second level index as I, user configurable parameter. Parameter is further explained in section 3. Each array of lists has an associated bitmap. Why are there multiple arrays of lists? First level array divides, second level subdivides as linearly. Number of parameter. Okay. One array, list of arrays. That itself contains. Is that correct? Information regarding block is stored. Figure 1 shows the two levels in data structure. First level, array of pointers. Point to the second level list of blocks. In this case, considering the bitmap first level, there are only 3 blocks of ranges. The 7 and 2. Bitmap of levels. First level, 4 second. Okay, so in order to easily blocks, the TLSF boundary tag 5 originally consisted in adding a footer field to each block, pointing to the beginning of the same block. The block is released. The footer of the previous block located one word before the release block acts as the head of the previous. Check whether match both blocks accordingly. It's possible to set boundary tag allocating not at the end of each set the header of the order to easily coalesce free blocks, the TLSF employs the boundary tag that originally adding a footer block pointing to the beginning of the same block. Okay. Block is really footer of the previous block. Located one word before the release block. Used to access the head of the check whether it is or not, merge both blocks accordingly. Okay. Possible to simplify the boundary tag technique allocating the head of the block not at the end of the block but inside the header of the next block. Therefore, each free block is linked to two different double linked lists, segregated list, blocks belonging to the size class, and a list sorted by physical address. So there is a footer in each block says where TLSF block header. Okay. The TLSF embeds into each block the information needed to manage the block, whether the block is free or not, and points. Link it into a list of blocks, similar sizes, and the list ordered by physical addresses. This data structure is called the block header. Okay. Since busy use blocks are not linked in any segregated list, their block header is smaller than the headers for free blocks. Busy use blocks are not segregated list. Their block header is smaller than the headers. Okay, you can see it. So a free block has size as the previous block, 32-bit, maybe just next free and previous free, which is a pointer. So we are on 32. So use block is just its size and the previous physical. Oh, and it also has 2 bits here. It also packs bits, which is C last physical and F block or not. Okay. Block header or free blocks contains the following data: size of the block required to free the block and to link this block with the next one in the physical linked list. Boundary tag. Pointer to the head previous physical. Pointers to link this block into the corresponding segregated list. The header of a busy block contains only the size and the boundary tag pointer. The header of a busy block contains only the size and the boundary tag. Block sizes are always a multiple of 4. The allocation unit is the word 4 bytes. You strip out those two and word. Two least significant bits of the size are used to store the block stack. Block is busy or free, whether the block is the last one of the pool or not. Okay, TLSF structure functions. Most TLSF operations rely on the segregated list mapping function. Given the size of a block, the memory function calculates the indices of the two arrays that point to the corresponding segregated, holds the requested size first level word. Second level in is I haven't really. This is the function can be efficiently implemented using bit search instructions. Do SLI. So SLI is level index. I don't know. I don't know. The first level index log2 size can be computed as the position of the bit of the size that is 1. Second level index, extracting the following SLI bits of size right word. For example, supposing a second level index SLI 4 and given the size 400. First level index, second level index. Why are they referring to second level index 4? That or they are space. So they want to allocate 400 correct? So log2 is apparently 8. Is that correct? Python 2 460. That floor is 8. Good. So that's 8. And then second level. Oh, sure. Okay, so so 8, this is, yeah, sure, this is 256, and we have to subtract 256 from that, so 2 to the 8. So this is what's left, and then we have to so that's 2 to the f, 2 to the l. This is 4 over the 8, 12.75. Why? Where is that? What does that even mean? Second level index can be by extracting the following SLI bits. Second level in. Okay, what does that? Does that mean we just 16 blocks? Okay, so this is a shift right, I, and shift to the left. So first a shift to the left by 4, puts it here. Then a shift to the right by 8, which puts it at the very bottom. Then also fraction of 200 and this. So this unsets first this bit, shifts it left by 4, and then shifts it down by 8 so that this is at the very bottom. So I wonder what this SLI. Okay, let's continue reading. The operations provided by TLSF are implies TLSF function will create the TLSF. The remaining part of the pool will be the initial free memory. Accepts 3 parameters, pointer to the size of the pool, second level. It is possible to create several in the TLSF structure. Function mark usable. Get a free block returns pointer to the free area of memory, requested size or bigger. Requested size is round. Operations. First step: calculate F and S head of the holding the closer class. Calculate F and S used to get the head of the free list holding the closer class segregated list. This list is not empty. Then the block at the head of the list is removed from the list, marked as busy, and returned to the user otherwise. Second step: search the next. Bigger than the requested size. Non-empty segregated list TLSF data structure. Search than the requested size. Segregated list in the data structure. This search is done in constant time using the bitmap masks and the find first set bitmap instruction. If a list is found, then the block at the head of the list will be used to fulfill the request. What? Otherwise. Search the next. If a list is found, then the block at the head of the list will fulfill. Since this block is bigger than the requested, it has to be split, the remaining inserted into the corresponding aggregate. And if free list is not found, then it fails. Insert a free block. Free list is not found, then the request fails. Insert a free block. This function inserts a free block in the TLSF structure. The mapping function is used to calculate the element as a segregated list where the block has to be. Okay. Coalesce blocks using the boundary tag technique. Head of the previous block is checked to see whether it is free or not. If the block is free, then the block is removed from the segregated list and merged with the current block. The same operation is carried out with the block. Once the block has been merged with neighbor blocks, new big blocks insert appropriate segregated. TLSF structure is characterized by three basic parameters. First level index is the number of first level segregated classes. Classes are a power of 2 apart from each other. FLI is dynamically TLSF initialization by the following expression. First level index block 2 dynamically calculated at the TLSF expression. Minimum of these. Second level index. Index subdivides linearly the first level ranges. For efficiency reasons, SLI should be in the range 1 to 3rd bitmap. Convenience SLI is expressed as the log to a division. Example by 4 subdivides each level segregated lists. Since the number of different segregated lists is determined by the value of SLI, the bigger SLI and the smaller the fragmentation. This is a user-defined parameter. Reasonable values are 4 or 5. Minimum block size. This parameter is defined to limit the minimum block size considering implementation reasons. MBS count set to 16. From the initial parameter FLI and MBS, some other parameters can be determined. So FLI memory pool size. Okay, so you're always getting the roundup here. Get a free block. Requested size rounded up to the just gives you the entire thing. This is also why you need to store the size in the head. Okay. I mean okay. Existing number of lists. 2 second level index, first level index. Minimum block size. So first level segregate. Make this parameter. I don't know. Whatever. Range of sizes accepted by each list. So 2 to the I plus I j, where all I and j natural positive numbers. The log to minimum block size less than or equal to I is less than the first level index. And j is the I is the first level index. And where next size is obviously next block, or this size of the data structure, whatever, we don't care about that. So where TFH is the fixed header of the data structure bytes and the PS is the pointer size bytes for a maximum pool of 4 GB, FLI is equal to, and I thought this FLI is the minimum of those two. And the maximum SLI is equal to 5. The size of the data structures required is 3,620 bytes. Pool of 32 megabyte FLI 25. SLI is 5, needs 2,800. Okay. Overhead of 3 and 2 kilobytes. Okay. Some additional optimization possible to search operations more efficient. This is achieved by using several strategies, cache and locality strategies. TLSF data structure has been organized as a level array and not as a bi-dimensional. This allows to take advantage of cache locality. Tests showed that this approach is more efficient than a bi-dimensional array. In addition, the TLSF data structure dynamically at the memory pool. This approach uses free memory but allows to have the TLSF. Yeah, so I wonder, how does it, well, if we free all, we get the pool, right? If we free all stuff, we in the end up with a pool, right? Whatever. We will see. Do we coalesce? Do we not coalesce? Do we defer coalescing? I mean, we want to write a tensor library, and we typically you allocate a bunch of tensors. Then in the end of the epoch, you free them all, and then you do it again, right? So it would be good if kind of cached. It would be good if it's cached and we don't coalesce. I don't know. Whatever. Bitmaps are used to track non-empty lists. The reason why FLI and SP are equal to 2. This allows to reduce accesses and to use instructions for search. Mapping function is follows. As said, this XOR. Why are they using XOR? What this? XOR well. Shifted. This is the subtraction. So let's say for really the subtraction, let's say 460 minus the 8. So we had that, that's 200. Correct. Okay. So we can also have 1 shifted right to the 8, which is the same thing, right? So verify that. Okay, but we also, oh, same thing. So an XOR, this is interesting. An XOR with this is the same as a subtraction. Why is that? That's okay. So that's one shift to right to the 8. This is 0. Okay, sure. That does make sense. Let's say 512. So this is not a subtraction. Not a subtraction. Why did it work for 460? Oh. So 512 would be a different. 512 would be 9. So also for 513, this would be 9. Yeah. So it is only the subtraction if they're in the range, right? Let's look at 460. How do you like 460? This is 256. So we see this bit is set in both of these. Now an XOR will just unset this bit, right? So that's a subtraction. That's why it's a subtraction sense. But as soon as the next bit is set, this one will no longer be a subtraction. It will flip this bit. It will flip this bit on, and it's actually then larger. Right? Then it adds to 6. Okay. So I see why that's possible. I don't know why you wouldn't just subtract. XOR cheaper than a subtract? I don't know. Think so. But okay. TLSF analysis. It is possible to obtain the time complexity of malloc and free operations from self-pursuit code. Malloc following. Point malloc, blah blah blah. Although malloc has to search in a TLSF structure, search block, this cost is 1, because to do search in a TLSF structure has always a constant response time due to instructions. The remove function simply unlinks the block from the segregated fit list, and the inserts in the head of the previous. What library in C will be used to make this? I mean, theoretically, you don't need a library to do this. Just write this. Try. Yeah, sure. So, remove function simply unlinks the block from the segregated fit list, and the insert function inserts the head of the corresponding segregated list. The pseudocode of free function is. Okay, so this is only then implementation. Fact that it does not perform an exhaustive search in the corresponding segregated list. Find a suitable block. Fill the request. The TLSF uses the mapping function and bitmaps to directly find the non-empty smallest segregated list. It contains blocks of the size or bigger than the requested one. Once the corresponding segregated list is found, the first block of the list will serve the request. Therefore, it may happen that there exists blocks big enough for a request but stored in the previous segregated list. One segregated list before the one returned by the mapping function. What? That I don't understand. The mapping function. First block of the list is of the request. Therefore, it may happen that there exists if big enough to pull a request but stored in the previous segment. Why? Worst case fragmentation. Biggest free, largest size segregated list. Biggest free size of free blocks. I don't understand that. Why would that be the case? Size is one larger than. Where's fragmentation? The biggest block has the largest size of its segregated list. Size of one word less than the minimum size of the next segregated. Application requests a block whose size is one word larger than the start size of the segregated list. One word larger. Start size. Starts. But it only compares the start size? Oh. But thought it maps all. One word larger than this segregated. I have no idea. TLSF will try to find a suitable block to request starting from the next step. Fully understand that. Okay. Fragmentation can be calculated. Okay. Assuming SLI is 5, the largest free block that will be in the segregated list, defined by F is equal to 12 and S is equal to 13, is 587. Here they explain it. $5,887. Search for a 5,701 byte block start in the segregated by f is equal to 12 and s 14 empty. What? Why is that? Possible to modify the TL to perform exact search, looping in the previous initial fixed time. Although this much no longer bounded. So largest free block that this equal to this. So they set all s is 14. Okay, let's this is it's doing I'm trying to read something on this dynamic memory allocation algorithm because I want to implement allocator for a tensor library that I'm trying to run. And right now I'm trying to understand what they mean with this. Like probably a minor detail, but yeah. So 7 bits, yeah. This is so 30. I don't know. S is equal to 14. Why? Why would and be 13? Second level. This. Let's calculate 5, 7, 5, 7, 6, 1 minus 2 to the 12 and then times 2 to the 5 over 13. What? Star is okay, this doesn't make any sense. Like, why this sense? If I calculate it with their formula, I get 13. Whatever. Okay, then they have their Guys, why are they the worst? Bold? Test summary. What are you doing on a big scale? Okay. What I'm trying to do is wait a second. Okay, I want to implement a work here. A tensor library. And so this tensor library has some functionality for math, for matmul, and so on. It has ways to reshape or like change strides, like change the shape of the tensor. And then we of course want something like autograd. So I want to build a graph. And then on the final node, I want to call backward. Then I want to get the gradients for all of the inputs, all of the lead nodes. So to train a neural network, for example. And the thing is, the basic fundamental thing we need is some way to allocate tensors. And the problem is that the lifetime of a tensor is pretty unpredictable. Now we could just use malloc and free. And that's okay. Could do that. But I don't want to do it. That's the explanation. And yeah, I want to then implement something that I can use instead that allows me to free individual tensors and allocate individual tensors. Yeah, something that I control and maybe then optimize if needed. Exactly, and I seem passionate. What motivates you to programming? Just an interest. To some, it may be something else, but yeah, I generally like doing it. Of course, not all the time, but so the next thing would be to try to implement something like this. I still have a lot of questions of how this works, and I don't know if they can implement. Kind of read through this. how do we start? So I want so where are the allocators in our here? We already have an arena. I also implemented the pool. Where is the pool? So I would also like to have the not here. But I don't know. Whatever. Okay. Maybe we know. Lips. Or.h. Okay, let's call this TLSF. Okay, the TLSF we need. What do we need? Previous. So we need a bitmap. Tells us ones are free, which ones are not. Correct. So first level bitmap, I don't know. This could also be just 32 bits. I don't know. Then we have 32 bitmaps. Kind of tell us also not known. Okay, we have like second level bitmaps, and then we have a this thing index. Let's call this first level index and second level index. I don't know. First level index was. We even need bitmaps. So FLI was not measured. So SLI is log2. Log2 SLI. And this is the direct. We have kind of like a minimum block size. This was 16. Make this. I think it was 6 in this page. Box size. this we have. Let's try to go into core. Go test. So let's start here. TLSF. Should we? I don't know. Maybe. So TLSF. TLSF in it. Create. And let's get a size. Also has stored in here. So we also kind of need a size. We may also want something like fit position. Separate. This is for the memory pool. And yeah. So size, let's say, let's get page. Size. And I don't even know how you ban someone. But you could just ban him. Ah, okay. Oh, I also know ban someone. Great. So, let's align the size to the page size. To size, and I've also got a guard page, so observe. Let's go total size, page size. This is pointer, base address. Just store this here, void start base address. Okay, so let's also page or yeah, we have to say like let's commit a page. Let's first assert that the size of a TLSF is less than the page size. Let's say TLSF is equal to TLSF base adder. TLSF size is equal to total size minus size of F. TLSF. Maybe we do it like this. F pause is equal to size of TLSF. TLSF. Pause is equal to size page size, and okay, so first level index and second level index. So they said that this is a zero parameter. So second level index, let's get this. Yeah, whatever. Let's just get it like so. And first level index, they also provided the int log2. Add a function for this. Yes, here it's index, it's just the size, and also said it said min this and 31, but I don't know why it is 32-bit bitmap. Okay, so depending on the first level index, we have to allocate some more stuff. I mean, at this point, I wonder whether it would be harder to wrap this inside an arena. I think that is what we do. No. TLSF create. Let's say this thing has an arena that makes you don't have to duplicate all of this stuff. And then we just say TLSF arena init and arena init the size, all this stuff. Don't need this. The arena and we just page size. What we can then do is TLSF arena push, call it arena push struct, arena push struct. arena, TLSF, TLSF. We say TLSF arena, arena. And now we have to push some things, right? So type def struct TLSF list. And it has a food or a block. Head type def struct TLSF block TLSF has a block, right? Let's call it free list. TLSF or maybe a free block. TLSF free block. Head. They also said detail the layout. What's the size? So 32 metadata. A previous physical block. This is, well, we have to define this as well. And whether this is useful for us or not. And TLSF free block next previous let's go sway manager user. Yes, true. Good. So we need this thing. TLSF free list and free lists. And we need how many need we well we need it has to be well, does the free list? No, I don't think so. Should the free list have the bitmap? Well, here it does, I guess. I don't know. Also, this then probably has to be well, we could start just here. The free maybe this second level. So we have to do something like arena push array. We have to push push TLS TLSF arena. So TLS list and first in that times. Do we do this? I mean, double check. We have to double check this stuff. I think maybe a +1 here. I don't know. Look at this. So this will be our TLSF. Has to be lists. And then each free list also needs its, oh, not each, segreg, how do we call these things? First level free list, oh, free lists, I don't know. So this only contains a pointer, but then we also have to initialize size less than second first level index. Oh. Num lists. Classes. Let's say this is first level +1. I actually don't know if that's true, but okay. So this is num classes. Classes plus classes. Num classes. And then we go through num classes. Get the TLSF. No. Say classes TLSF classes at I class entry, and we have to set this pointer. Let's just do it like this. Equal to arena push array TLSF arena TLSF free list, but this time it is actual free list, and it is second level index. So this is the number of linear segregation. Number linear seg second level. Yeah, I don't know. And then we do int log2 for linear segregation like this. Second level. Second level free lists. hate this name. Okay. Second. And this, yeah. So this seems like the initialization. Does it work? I don't know. Then we return the TLSF as well. Funny is all that. Yes. So this is a doubly linked list. I had macros for single link, for lists with a single link, SLL, push, up. We also need this for a doubly linked list. DLL push name SLL DLL. Good. So DLL push name. The question also is, like, does it have a last one? Doubly linked list, does it last? And also need a pre name. We need, could say okay, no. Set list head name read name to our node. Think. Okay. From the head. Head name. Also list leave name. That's the but leave. Okay. We also have to initialize these things, right? So CLSF they're just push array 0, and we don't. CLSF relay. TSLF. Okay, maybe, or let's see, main. Maybe design a test for a doubly linked test. Wait. Test. Let's get an arena. Let's create test for type dev struct e struct I a b, go through these. I is less than 1000 plus. Say okay, arena push struct e are have an AB list. Let's say this also has an AB star next, AB star prev. List. AB list has a head, and say AB list our list. Entry DLL push list this, and go through all of these. Let's just first say okay, entry A is equal to I, entry B is equal to I plus 1, and then we go here and then we say a LL top test list, and this is AB star entry. Let's assert A is equal to count and then entry A is count minus I minus 1, right? Count minus I this, and let's also test that. So I'll test. You can also do the same thing for a single linked list as a next pop this s, and we build this. No member. Maybe because ready. Oh, no member. Oh. Core.h. DLL. What was it? Pop. Not prev name. It's prev head name. Prev name. Okay, it hits a segfault. This is great. Cannot push. Prev access. Entry prev access. What is I? Is 0. So there is a problem. Sure. Because head is null. So if list head name think still. And now it's in DLL pop. Entry next pre entry next pre. If there is a head, if there is a prev, no entry. Entry next. Where do we do that? If there was a head, new head comes next. Okay. So this may be the previous. No. No. Okay, head can get null process. Okay, so if list head name regard here as well. And now the test passed. Okay, let's see. We can also delete stuff in the middle, but which we can right now. We just access the head and push onto the head. But okay. Let's do it. Edit. Let's have structure. Good. Yeah, I think that's it for now. We have to get into this stuff and how we exactly implement it. But I think that's for another day. So I hope you enjoyed it, and I'll see you on the next one.